What are the relationships between motion graphs? Your warm-up was mostly a review from the post-lab from our motion graph lab. The slope of a displacement time graph gives you velocity, and the slope of a velocity time graph gives you acceleration. If you were absent on Thursday, you don't have the coefficients from Thursday's lab, but if you were here, all you had to do was write them down to keep them fresh in your mind. Okay, so people still have questions about acceleration, so this is the point where we broke off and we went and talked about acceleration. When we came back, most classes we did a review from what should have been your reading prior to Thursday's class and what we talked about today. So acceleration is a change in velocity. Deceleration is a special case of acceleration where it is opposing the velocity. So the magnitude of your velocity will be decreasing. Acceleration is a vector. So a positive acceleration is an acceleration vector that is positive in your frame of reference. For negative acceleration, it's acceleration that is negative in your frame of reference. Okay, if you missed class on Thursday, please make sure you go through the presentation about measuring acceleration from Thursday, September 25th's assignment page. Okay, so now we're back to where we want to be today. How do we figure out displacement from acceleration? I'm going to pick an acceleration versus time graph that looks like this. Some constant acceleration. I'm going to choose this with a positive acceleration because we're going to be dealing with area, and it's easier to start out visualizing area as positive numbers. Okay, here's that same graph from the previous slide. All right, and here's my definition of average acceleration, delta V over delta T. Now that's just a relationship, so I can rearrange it to solve for delta V. Average acceleration times change in time. In this case, my acceleration is constant. So my average acceleration is the same as that value A over there on the left axis. Okay. Now, to find that, graphically, that's just a rectangle on this graph. Okay? And the area of that is base times height. So delta T on the base and the height is the acceleration. Huh, that's my delta V. Okay, now here's the velocity graph. The pale green horizontal line, all right, that starts at V0, is just to show you that if there was no acceleration at time TF, my final time, my final velocity would be the same as my initial velocity. Instead, I have increased by the shown delta V. Okay? And because we know from our previous graph that acceleration is constant, the slope of my velocity graph must be constant, which makes it a straight line. Okay, so now I have a straight line. I can write this equation for this line, okay? So essentially I end up with the function of my final velocity at whatever final time I'm looking for as my initial velocity plus acceleration times time. Now, if my acceleration initially had been a negative number, we would have taken the area underneath the x-axis, in which case you can see that my delta V would have been negative and my final velocity would be less than my initial velocity. All right, we're going to stick with our original graph of velocity. Here it is. And here's my definition of average velocity, delta x over delta t. Again, I can just rearrange this, but now my velocity is not constant. So if you remember that if I have a parallelogram, which is the shape formed between time equals 0 and TF underneath my velocity graph, if I took TF divided by 2, okay, that's going to be the average, that velocity there would be my average velocity in that time span. Or, here's how we can do this graphically. If I hadn't accelerated, here's that area, okay? So V0 times delta t, and then that's just a triangle that's left. So the area of a triangle is 1/2 base times height, or height times base, either way. So I can rewrite this delta x as the area of the rectangle, v naught times delta t, plus the area of the triangle, 1/2 delta v times delta t. Okay, now we saw during our lab on Thursday that something with constant acceleration is going to give us a parabola for a displacement graph. Something like this, depending on where your x naught is. Okay, but this doesn't look like a quadratic. There's nothing squared here. So I'm going to drop the deltas from my t, because if we assume that my initial time is 0, then I can essentially start writing this as a function of time. I'm also going to plug in, for my delta v, I'm going to plug in acceleration times time. If the parentheses confuse you, please remember that since this whole term, 1/2 a times t, that's all multiplication. So the parentheses, you could take them out. They don't matter. It's not a plus inside the parentheses, so there's nothing to be distributed. Okay? All right. Now I'm going to simplify this. V naught t plus 1/2 a t squared. Now that looks like the equation for a parabola. But it's not quite a function because I still have delta x at the beginning. So if I remember that delta x is xf minus x naught, I can add x naught to both sides, and all of a sudden I have something that is in the form of c plus bx plus ax squared. Instead of x, it's t. And you might notice that there are 3 coefficients. To correlate these to our lab from yesterday, x naught would be your coefficient c. That's where you started in relation to the motion detector. Your coefficient b from yesterday was your initial velocity. You should have gotten a negative velocity yesterday for your coefficient because you started by throwing the ball upwards. And then your coefficient a from yesterday should be 1/2 of your acceleration. Now, if you remember from IPC or anywhere else that the acceleration due to gravity at the surface of the Earth is about 9.8 meters per second squared, or call it 10. So if I divide that by 2, your coefficient yesterday should have been somewhere around 5. All of you were somewhere between about 4.5 and 6. That's pretty close for a lab where you didn't know what you were coming up with. So, hopefully, this makes those coefficients make a little bit of physical sense. We also now have kinematics equations for motion with constant acceleration. I have both position and velocity as a function of time. Okay, but what if I have a problem where I don't have enough pieces of information to solve one of those? Like, what if they don't give me a time? Well, there's some complicated math, and this uses the fact that if acceleration is constant, then your average velocity is your initial plus your final over 2. We're not going to worry about that. You're not ever going to have to derive this. See, it says it here. I just want you to know that this isn't magic, that there is math, okay? And this is where it comes from. So here are your kinematics equations for motion with constant acceleration. These 3 equations are on your AP equation sheet. I do recommend that you memorize them. And I hope that you have some physical understanding of what the first 2 mean. The last one's just a tool for solving kinematics problems. Okay, side note. These 3 equations only work if acceleration is constant. Otherwise, that very first area we did is no longer a rectangle, and the rest of the math doesn't make sense either. Okay, so if my acceleration is some number, or 0, these equations work. Remember that 0 acceleration is still constant acceleration. In that special case, that first kinematics equation, if I plug a equals 0, that t squared term goes away, and I'm left with this. Makes sense. In this case, my velocity is not changing, so it's v times t will give me the distance I traveled, right? And then, so wherever I started plus that distance is going to give me my final position. There's also a special case of the kinematics equations for a case called free fall. When only gravity is acting on something, and it is only traveling straight up or down, so one-dimensional motion, like we're doing in this unit, we're also neglecting air resistance, because when that's there, our acceleration is not constant and these equations don't work. We'll get to that later. All right, you can plug all these in. So instead of x, we use y, and for acceleration, we use g, the local acceleration due to gravity. Now, if you define up as the positive direction, you absolutely must plug in g as a negative number here. And then all those pluses for the last terms in each equation become a minus instead, okay? Please do not forget that part. Here's the summary of concepts. The area between an acceleration graph and the x-axis gives you the change in velocity. If it's above the x-axis, it's a positive change, and if it's below, it's a negative change. Same idea with velocity and the x-axis, except then it's the change in position, also known as displacement. You will have to solve problems from a graph using these concepts, but you will only be given rectangles and triangles under the graph, or combinations of those that you can solve geometrically. Please read section 2.5 in OpenStax for your homework. Also, watch the acceleration video lecture and take the video quiz on Moodle. It is not a mastery quiz, it is a homework grade, and it closes at 9 a.m. on Monday. Please also start working on your problem packet, but we will have time in class Monday to ask questions.